Okay, thank you everybody. Good morning. My name's James Wakefield and I'm from the University of Northumbria, and I'm presenting this morning on behalf of myself and my research colleagues Omar, Pablo and Mohamad, also from Northumbria, with the exception of Mohamad, who is from Newcastle University in the UK. The research that I'm presenting today is concerned with the as-built environment rather than new build construction. And my principal concern, or the principal concern of the paper, is about the fact that we need to upgrade the existing built environment, and we need to make sure that those buildings that are not as carbon efficient as they should be are brought forward into the future domain and are able to be retrofitted with new technologies which make them fit for the future. In terms of the research that I'm presenting today, having given the context there, the research is underpinned by 3 case studies. The first case study involved looking at a smart energy project in the UK called the Smart Energy Network Demonstrator, and together with a group of health and safety experts and experts in the smart energy domain, including from the manufacturer of the hardware that was installed to enable the smart energy network in this case. This was Siemens representatives. We went round and we assessed essentially how is the environment changing in terms of the way that we are overlaying smart technologies and so on, in order that the buildings that we already have can become more energy efficient and can help us with our carbon targets. And what we found there as part of that first study, as part of the pilot study, the first of which that underpins the research I'm talking about today, we found a new hazard profile. So in very simple terms, with the Smart Energy Network Demonstrator, which is a smart energy network, lots of building control, hooked up to a solar field and wind turbines and so on and so forth, lots of battery technology. We found radio masts were being installed at scale across the network installation. This means that more construction operatives and maintenance operatives will need to go up and be on roofs. The same for solar panels on roofs. The maintenance of those panels is going to put more people on roofs. So the biggest or the predominant hazard concern in the UK being fall from heights, the biggest construction-related killer. We're actually, as we're upgrading the built environment, we're going to be creating an enhanced hazard profile, not necessarily new hazard, but more instances of the same, in this case, fall from heights. And so it's important then that we look to technology to help us understand how we can go about mitigating against that new hazard profile. The second of the pilot studies involved looking at a hydrogen into gas solution in the UK. Hydrogen was being injected into the gas network at a rate of 20%, and this required, this was experimental for the UK, and it required a change in the regulatory arrangements specifically for that network. So we asked questions of the network operator and other health and safety experts who are involved with that project. How does this change or enhance the hazard profile for those people that are responsible for maintaining and implementing those kind of solutions? And what we found is that the hazard profile is advancing, changing, and the suggestion was that we need some kind of technology-enabled solution to deal with that advancing hazard position so that we can be sure that our construction operatives who are visiting those estates to manage and maintain them are safe. We then looked at a third pilot study which looked at a fairly innovative solution with a UK retailer whereby hazard training was in some way personalised to the individuals that were responsible for coming and maintaining that estate. And that links then to site access verification protocols for those construction operatives, meaning that the hazard that they are likely to face when visiting the estate is mitigated against with the hazard training that is presented to that individual prior to them being given access to the estate. So that gives you something of a flavour of the background and that which underpins the research. We then went on to look at the problem in the context of the existing literature, and we find flatlining health and safety outcomes in the UK construction sector, which is a concern regardless of these new smart technologies which we're overlaying to the existing built environment, which I just mentioned. The papers suggest bring new hazard and new concerns. We see also in the literature a case for technology as a safety enabler. We see BIM still fairly early stage in terms of its ability to perform as a safety enabler in the construction space, both new build and as built. And then we start to see ontology development approaches in terms of the innovative solutions that have been applied in this safety for construction space. Moving on from that, through that ontology development for construction safety research, we start to see the ability of those researching in that space to start to personalise and contextualise safety information for construction workers as well as construction managers working at planning level and so on. And so the idea is that through this research that is taken forward such that a specific solution, the nature of which I alluded to earlier, can be developed. We then went on to develop an ontology of our own, and that ontology was designed to underpin a construction safety framework, and that construction safety framework is itself designed as an enabler for a site access verification solution. And ultimately what we were working towards here was a situation where it was possible to say, where is the individual construction worker going? What is it that they are going to be doing when they get there? What elements of the building may they be working on? What is the hazard which is existing there? What area of the building are they going to be working in? And that enabled us to create a situation whereby using the ontology as a way to build knowledge of the domain that we were proposing to deliver the solution via the framework, that ontology enabled us to create an understanding of the delivery environment. So what does the delivery environment look like? What are the various classifications in that delivery environment that would be relevant to that which we're trying to achieve? Where is the data existing currently? Is there any data that we would need in order to enable our process that doesn't currently exist in the delivery environment? And so you can see from the ontology on the left, which lays out those data classifications and codifies the relationships and dependencies that exist between them, we were able to go on to develop a framework. And that framework has 4 key domains which are reflected in the ontology. Built asset domain, that's informed by a BIM element. So we demonstrate how we can use an information model in using the BIM process to allocate hazard to the environment such that it can be queried according to the specifics of the job which exist in the job domain. We then have a hazard domain where we deal with the hazard as has been determined by the ontology in this case, according to the information or the data that is inputted. And then we have a related access domain, which ultimately controls the access of the individual to that built estate according to credentials which are set through the ontology. Those credentials, by the way, are linked pretty straightforwardly to hazard training, which is then allocated to the individual profile. So if we detect a fall from height hazard, then it is possible for us, according to how we configure the solution, to make a short hazard training, maybe video or something of this type, as a credential for that individual to be able to get access to the built estate in this case. Here we can see the ontology implementation, and so this was undertaken using Protégé. And what I'm trying to demonstrate with this slide is that we can input data into that ontology, and we can say if job is ID star 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 in this case, if user is X, the area is roof, and so on and so forth. You can see there on the left. We can then query the information model for the hazard that has been identified and stored there. And then what we can do is we can output a hazard profile, which ultimately can be made to correspond with some hazard training. It's self-set for the individual as a credential for access to the site that they're trying to come and work upon. The findings then, there was a rationalisation of the problem. There was a suggestion that more complexity in the built environment leads to an enhanced hazard profile at operation and maintenance phase. Through the ontology and the linked profile and the associated solution, we made a technical demonstration of a BIM-driven and learner management system-enabled hazard safety training personalisation process. Of course, there were limitations. Only partial implementation of the ontology was made. This was a technical demonstration rather than a fully functioning site access verification solution. We identified that there would be challenges around how we arrive at hazard data, how we organise it, how we maintain it in line with UK regulatory frameworks in this case. And the future work will be around, or already has been in fact, for future publications, will be around existing ontology integration to the ACVER ONT. That's the name of the ontology that's been proposed, by the way, access verification ontology. And a full evaluation of ACVER ONT and the related framework. Thank you very much for your time.